So the final talk for today, SNIP, Speculative Execution and Non-Interference Preservation for Compiler Transformations, with a subtitle that I let Sören read.
All right. Does the mic work? Yes, all right. So, yeah, it's the same idea of the previous talk. We want to secure compilers, but we will introduce this step by step. So let's talk about SNIP. And we start with the S, which is speculative execution. And the thing that we want to protect from is spectra. And spectra has this nature, as we have already seen a bit in some talks, that in typical semantics, we do not see it, because typical semantics models program counters, registers, memory variables, but spectra works on microarchitecture, on caches, branch predictors, and all that kind of stuff. So this is an example we have seen already. It's a bounce check followed by a load, and then we use the loaded value as an address. So how does the program step through this with speculation? If we're in this state, we should have an out-of-bounds access, and our if should go wrong, but speculatively, we might execute this statement nonetheless, and therefore load our secret A if we align badly to our register A. And then in the next line, we use our register A with a secret in it as an address. Eventually, our processor, however, will catch up and roll back to the initial state, so A has no longer the value of the secret. However, we have side channel leakage, and this is where we model the leakage in our semantics, that if we have a conditional, we leak the value that we evaluate the conditional to, and if we have an address, we will leak the value that your address has, because we created a cache entry at that address, and that's visible to the attacker. So in the last line, where we use our secret as an address, we will see this in our semantics. Now, branch prediction introduces non-determinism, so we have a different second side to our microarchitecture, and this is the part where our attacker can set up the microarchitecture to guide our semantics. So we have a directive that tells us, just as in the previous talk, when we have a conditional, it tells us either to mispredict or to predict correctly. In our example, we mispredicted, so we have a miss here. When we have a memory access, we also give this power to the attacker, because we are memory unsafe. We assume the attacker to know the memory layout and the programmer to not exactly know the memory layout. So we give, in this case, the attacker the chance to steer this out-of-bounds access to align with our secret. And then, as we have seen before, if there's nothing to steer about our instruction, we just have a step as a directive. And that removes the non-determinism that comes with speculative execution. Okay, so in general, what we have is an architectural state. We receive a directive from our microarchitecture, we execute our transition, and we observe some leakage to the microarchitecture. And therefore, rather than having to model all the microarchitecture in our state, we can just move our, this should look different, we can just move our microarchitecture only to the semantics, so only to directive and leakage. Okay, so that was the S part. We have semantics, and we can model, we can observe spectra attacks in our new semantics. So SNI is a property that proves absence of spectra attacks. This is what we have seen in the last talk, so I'm going to be quick. We have a state, an initial state, and we divide it into a public and a secret part. And when we have a second state that is equal on the public part, we say it's indistinguishable to the attacker. SNI is a non-interference property that says, okay, give me any two indistinguishable states, and any sequence our attacker might steer our program through the microarchitecture, so any sequence of directives. When we execute either of those two states on the sequence of directives, we should get the same leakages, because then our attacker cannot observe anything about our secrets, because it's the same sequence of leakages. And then for compilers, what we would like to have, if we have source-level semantics that can model spectra attacks, and we have ensured, here's our source program, it has no spectra attacks, it is SNI, and we run our compiler on it, we would like to have our target program also to have no spectra attacks, so to be SNI. And then we say our compiler is SNIP if it does so for all programs that we can use in our source, as a source program. Okay, let's look at an example. And this is our example is register allocation, with the source program being this program. So we have a bounce check followed by a store of a secret into an array, and then we access our array at int. It is SNI because the underlined positions are the only leakages, and they are dependent on public variables, which are not overwritten in our program at any time. Now, register allocation will move some of our registers to the stack because there might not be enough space in our target register set to keep all of them as registers. For example, in our program, we could move int to the stack initially and restore it right before our usage. And the question is our target program now SNI or not? And the answer is not. There's a spectral tag in there, and it follows from the following sequence of directions. So let's go through it with a state. We have our secret here as 42, and the first instruction will just put int to our stack, which will become 0. The second instruction is a misprediction, and since 20 is greater than 8, we will execute this instruction speculatively, and there we store our secret to wherever our attacker likes, basically. And our attacker chooses to align our out-of-bounds test just where our int is stored on stack. So when we restore int from the stack, we will restore 42, and we have a new information flow that was not possible in the source program, which leads to our secret being leaked in the target program. All right, this means that register allocation is not SNIP, which partly answers the question from the previous talk, and we did reproduce this with LLVM, actually, and all of LLVM's allocators on code, which is from libsodium's cryptographic library. Okay, with that, our motivation is done, and we can look at two goals. The first goal being, how can we prove if we have a of which we are sure that it is SNIP, how can we prove it? And the second question is, can we fix register allocation, which we have just seen to be broken, so that it becomes SNIP again? And for this talk, I'm going to focus on the first question. We will do so by example, which is that code elimination, and the reason being that it is SNIP. So before we go right into SNIP as a preservation, we want to do safety preservation first and look at how people prove safety preservations for programs. Here's our example program. It's a bounce check followed by a load, and then we discard the loaded values because we overwrite it by 0. So that code eliminator would probably detect this and replace the instruction, for example, by a no-op. Now, in order to prove safety preservation, what we usually do is we use a simulation relation that relates target and source states. So in that code elimination, this relation would just state that we have equal states except for the locations that are dead because they do not matter. So as an example, here we have two states. They're equal on all live variables. Just A, which is dead, has different values, so they're in relation. Simulation relation have a second property, and that is the replay property, so that if we have an execution in our target state, we have to be able to replay this execution in a source with the property that afterwards we should end in simulated states once more. And this is the case because even though A is now live at the end of the program, we have equal values between source and target program. All right, so this I call the simulation square, and it induces something I call simulation intervals, which means just stepping a few steps in the target program and some in the source program so that we are in simulation once more. And the nice thing about the simulation square is that we now can do our proof inductively along the source code or along source and target code by just applying our simulation squares once more, and so a whole trace and target program can be replayed in the source program. And indeed, we get a theorem, which is not by me, but it's older, that states if we have a simulation between any source and target program so that the simulation square holds, we get for any safety property that it is preserved by. Usually this is a parametric in P, so that we don't have to create a simulation relation for every source program once more. And another nice property is that we can do our proof without knowing the safety property front up. And we don't even need to know whether this program satisfies it or not. All right, with that, let's look at the advanced version where we move to our speculative semantics. And the naive way would be to say we have our simulation square, we have a semantics, which is new. Let's just plug them on, right? Here we have it. If we have a target execution with directives D and linkages L, we need to reproduce that on the source program. Let's look at our example. Let's look at two states that are in simulation, and let's execute something on the target program. Namely, we do the correct branching. I is this time 4, which is less than 8, so we have an inbounds. And then for the knob, we will get the directive step because microarchitecture will not influence a knob. Now in the source program, what we will see is first instruction is easy, we can just replay it, right? Second instruction looks like this. We have a step through our load, which will produce some leakage, and that means we have different leakage between source and target program. Here's another pair of states. We already mispredicted. I is this time 20. And then in a target program, a knob stays in knob, right? Still a step, directive, no leakage. In the source program, we have an out-of-bounds access, and that means our attacker will give us a directive. So we have also a mismatch in directives. So rather than the diagram as we had it, when we receive directives and leakages in our target program, when we're playing, we will actually see different directives and leakages. And with that, we can move to SNI preservation, so SNIP, which told us, okay, source program has SNIP, then target program should be SNIP. Let's look at our example once more, and let's ask ourselves, is our target program SNIP? In order to do so, we will have to look at any pair of indistinguishable states, as an example, these two, and we will have to execute any sequence of directives. In this example, these directives. And then we observe the leakages of one of the states, and in order to be SNI in the target program, the other state must have the same leakage. In this case, it's the case, but we would like to prove this. And we would like to prove this in a way that is not, okay, observe look at the full target program and check whether it's SNI, but rather we would like to check this in terms of the source program. So what we do instead of just looking at our target program, what we do is we create a simulated state of the initial state in our source program and a second one for the other state. These are also indistinguishable. And we translate our directives using our simulation square that we already have. Okay, in this case, this would be this sequence of directives, and we observe some leakage in the left state. Now, we don't even have to think about the right state anymore because we know our program is SNI. We know it has to have equal leakage, and this is the case. Okay, a little bit more abstractly, what is our job? Our job is when we have two indistinguishable states in the target program and two indistinguishable states in the source program that are in a simulation relation, and we execute one program execution in the target program. What we have to do is we have to prove that the other initial state has the same execution with the same leakages. And same execution meaning on the same directives. And in order to prove this, what we can rely on is by simulation square, we can obtain a source trace. And by SNI, for the source program, we know that the second indistinguishable state in the source program must have equal leakages as well. So we can rely on the black part in order to prove the purple part. However, we wouldn't want to do this holistically, but just as we had done for the simulation square, which was an inductive principle which we could move down, we want now to do this for our cube. And this means to look at like a slice in our diagram. When we zoom in a bit and move the frame out of the way, it looks like this, right? It's more or less the same shape. However, we have an issue here, and the issue is that when we look inside the target program and inside the source program, we have something, what is this, right? How do these relate? So we have two states inside the source program. In our original diagram, this was an indistinguishability relation. However, this is only defined for initial states, so we have to do something else here. And the something else is same program counters. So when we have two states, we say they are it's the same program counter when they share the same program counter. And the nice property is this is nice for our induction because initially we have our states to be indistinguishable. They're initial, so they are the same program counter. So with that, we can rely in induction on the upper part, and we have to prove for our induction to go through that this also holds after our cube executed. Now, I'm not going to go into detail for how we prove the same program counterness. It's actually something that follows directly from the semantics, because our leakages leak the program counter. So when we have same directives and same leakages, we will actually end up in the same program counter. So that's moving out of the way. And this is a property that we need to get out of our simulation relation, right? It has to satisfy this cube in order to maintain equal leakages. So we get a similar theorem to the previous one in our paper, which states that if we have a simulation relation between source and target program that satisfies both the simulation square and our new designed simulation cube, then we get that our compiler satisfies SNIP. And again, we don't need to know anything about the source program in terms of whether it satisfies SNI or not. We just define our simulation relation parametrically in P and prove our simulation square and simulation cube. So let's have a look at the proof effort that we need to do in order to apply our theorem. First, we have to define our simulation relation, which is the first step. Then what we have to do is we have to look at the directive. And a nice way, as we have seen in the previous talk, is we could employ a function in order to translate the target directives to the source directives. And as a last step, what we need is to rely on this equal source leakage to prove equal target leakage. And again, as seen in the previous talk, we could employ a function here that translates source leakage to target leakage. All right, so in our paper, we applied this method to that code elimination in order to prove that it is SNIP, and then we tried to do it for register allocation. However, already the first step failed, and that's not surprising because we have seen earlier that register allocation as such does not satisfy SNIP. All right, so this answers our first question. Yes, we can prove this with a simulation relation that satisfies the cube. And for the second question, I mean, we don't have much time, so I'm just gonna delegate you to my press talk on Monday, which is recorded. So I encourage you to just look up there how we can fix our register allocation so that it does become SNIP. And this I will take ahead, it does become SNIP. So to wrap up, we've seen semantics that can model spectral attacks without having to pull all microarchitecture in our state. We have seen SNIP as SNI as a property that will guarantee that there is no spectral attack in our code, SNIP as a property to convey this through the compiler, and we have seen how to do it by use of a simulation relation that satisfies a simulation square and simulation cube.
We have some time for a question or two.
Very nice talk.
Thanks.
Does the new register allocator lose anything in performance?
Yeah, you have to lose something in performance. So the way I can give you a broad idea on how it works. So what we do is we just take the register allocation as is and run it through. And then we have leakages in our target program. And in order to fix it, what we do is we build a synchronized program between source and target program in order to detect where information flows happen in the target program that don't happen in the source program. Then we statically perform an analysis that will tell us which locations can have different values between source and target program. And those we need to protect.
Hi, nice talk. I was wondering if the extra generality you have with respect to the previous talk buys you something in terms of proving, or you always instantiate these relations between directives and observations with just functions?
Yeah, so I think it is similar. I think Santiago said to me once that his method is complete, so I think we should not have more expressive power with my proof method.
I see. Okay.
Yes, and it's also reasonable to define it as a function, and so I didn't come to any occasion. So if it's complete, I think we don't need anything else.
Okay, thanks.
There's one more question down there.
Thanks. So I wonder, the target traces, do you assume, so you say they have the same program state, the same program pointer?
Program cutter, yes.
Yeah. So you assume that on both target traces you are making the same speculative decisions?
Yes.
How is that, why can you do that?
You mean why can't the attacker choose different directives on the two traces in order to learn something about secrets? Now this is a very good question because I ask myself this as well, and so far I have not found a convincing answer. The thing is, like the property I'm looking at is not one I thought of myself, right? It's an established property, and this property requires that. So it would be interesting whether there is like something going on. However, my argumentation for it at the end was, if you're an attacker and you execute your attack, you will use one secret of directives, and then you probably know at what point to observe the correct leakage, right? So this is how I would design an attack. So this is probably not the answer that is most fulfilling, but it is maybe at least a hint at why this might be not a bad idea.
Okay, thank you.
Let's thank the speaker again, and this concludes the conference.